listen-only mode.
Hello everyone, I'm Gail Warren with the National Renewable Energy Laboratory, and I'd like to welcome you to today's webinar hosted by the Building America program. We are excited to have Bill Zoller, Dave Millay, Jordan Dents, and Francis Conlon joining us today to continue our series on strategies to improve the performance of heating, ventilating, and air conditioning systems for low-load homes and home performance retrofits. Before we begin, I'll quickly go over some of the webinar features. For audio, you have two options. You may either listen through your computer or telephone. If you choose to listen through your computer, please select the mic and speakers option in the audio panel. By doing so, we will eliminate the possibility of feedback and echo. If you select the telephone option, a box on the right side will display the telephone number and audio PIN you should use to dial in. Panelists, we please ask that you mute your audio device while you are not presenting. If you have technical difficulties with the webinar, you may contact the GoToWebinars help desk at 888-259-3826 for assistance. If you would like to ask a question, please use the questions pane to type in your question. Please indicate to which speaker you are addressing your question. If you are having difficulty viewing the materials through the webinar portal, you may find PDF copies of the presentations at the website listed here, and you may follow along as our speakers present. Today's webinar is being recorded, and the recording will be available on the DOE YouTube channel within a few weeks. We have an exciting agenda prepared for you today that will focus on strategies to improve the performance of HVAC systems for low-load homes and home performance retrofits. Before our speakers begin, I will provide a short overview of the Building America program. Following the presentations, we will have a Q&A session, closing remarks, and a brief survey. The U.S. Department of Energy's Building America program has been a source of innovations in residential building energy performance, durability, quality, affordability, and comfort for nearly 20 years. This world-class research program partners with industry to bring cutting-edge innovations and resources to market. Building America is supported by 10 industry research teams and 4 national labs. Each of these teams and labs partner with dozens of industry professionals, including builders, remodelers, manufacturers, and utilities. The best and the brightest in the residential buildings industry can be found here. Building America uses applied research to deliver building science solutions using a 4-step framework. These innovative solutions are tested in homes to develop proven case studies of success the market can point to. Building America provides the tools the building industry needs to ensure the innovations are applied correctly, always keeping an eye on energy performance, durability, quality, and affordability. The final step, infrastructure development, is the conduit to getting innovations to the marketplace. Building America research focuses on how the components of new and existing homes work together through systems integration. As the market changes and evolves, so has the direction of our research in order to add value and drive changes in performance across the residential building industry. In addition to technical challenges we've been addressing for decades, there is now a need to understand market transformation issues, such as evaluation of energy efficiency. In the 20 years of Building America research, we have spearheaded combining ultra-high efficiency with high performance in both new and existing homes, and we are consistently achieving this challenging task. For example, in 1995, a typical home used 3 times more energy per square foot compared to today, and indoor air quality, comfort, and durability problems were common. Today, a home built to DOE Zero Energy Ready Home specifications uses less than half the energy and is more comfortable, healthy, and durable. By 2030, Building America will demonstrate that new and existing homes can produce more energy than they use. Do you want to know more about these proven innovations born out of world-class research? The Building America Solutions Center is your one-stop source for expert information on hundreds of high-performance construction topics, including air sealing insulation, HVAC components, windows, indoor air quality, and much more. You can find it by the URL on your screen or by searching on Building America Solutions Center. Also, the Building America website provides information about the program, the latest top innovations and case studies, and there you can also subscribe to the monthly newsletter. And now on to today's presentation. Our webinar today will focus on strategies to optimize the performance of HVAC systems for low-load new homes and home performance retrofits. If you would like more detailed information about any of these efforts, or if you are interested in collaborating, please feel free to contact any of our presenters. Our first speaker today is William Zoller, a senior architect and researcher at Stephen Winter Associates. Bill has 30 years of experience in building design, new construction and retrofit, post-construction evaluations, tech transfer and training, and building materials development. Today, Bill will provide an overview of several design options for locating ducts in conditioned space, including those ducts in unvented attics, dropped soffits, integrated into modified truss and floor trusses, and sealed crawl spaces, as well as varied and encapsulated ducts. Next up is Dave Millay. Dave is an engineer at Home Innovation Research Labs, where he focuses on evaluating residential HVAC and building enclosure systems and designs. Our next presenters are Jordan Bentz and Francis Conlon. Jordan is a vice president at the Levy Partnership, where he develops and manages building science research projects and consults for building owners and operators. Francis is a mechanical engineer and construction consultant at High Performance Building Solutions for energy-efficient construction, air barrier systems analysis, building envelope commissioning, HVAC systems, indoor air quality, and moisture management. Jordan and Francis will discuss a project with two retrofit duct sealing techniques, manually applied sealants and injected spray sealant, that were implemented in several low-rise multi-unit buildings. They will also compare the results of the two methods in terms of reduction in duct leakage to the outside, cost, energy savings, and payback. And with that, I'd like to welcome Bill to start the presentation.
Thank you, Gail, and hello, everybody. As Gail mentioned, my name is Bill Zoller. I'm a registered architect with Stephen Winter Associates. We also manage CARB, which is the Consortium for Advanced Residential Buildings, through the Building America program. I'm going to be doing a presentation on design options for locating ducts within conditioned space. I do have a lot of slides. I'll be going through some of them pretty quickly. A lot of this is an overview, and since there's a lot of options that are worth considering, we need to make sure that all of them are given a little bit of presentation time and a little bit of description. Next slide, please. Okay, so the primary question is, why are we concerned about putting ducts in conditioned space? And if we look at what the typical option would be without putting ducts in conditioned space, basically ducts located in unconditioned attic spaces. And when we look at attic spaces in the south, for instance, we could have temperatures of 160 degrees, and in the north, temperatures of, say, 0 degrees. And when we're putting cooling air through ducts at 55 degrees in 160-degree space, obviously there's some thermal problems that are going to occur, thermal losses. Similarly, with 150-degree, 140-degree heating air through a space at 0 degrees, that's a huge delta T, and tiny little leaks and losses can result in huge thermal losses. We've seen losses range up to 45% or more, so they can be very, very significant in terms of losses. There's also problems with indoor air quality. If we've got leaky ducts in an attic space, we've got pressure imbalances in the house that result, moisture problems, comfort problems, and ultimately durability problems. So all that stuff is something we'd like to avoid. So we come up with some options to do just that. Next slide, please. What we've got is a series of options that give us alternate places to put our HVAC systems within the house that basically limit those thermal losses. So basically, we're trying to thermally protect our duct systems. And we'll be looking at actually 6 different systems. There's 4 located on this slide right here: ducts in unvented attics, drop ceilings, modified trusses, ducts in floor trusses. We'll also be looking at basement applications in unvented crawl spaces or unvented crawl spaces, as well as buried ducts. And the reason we have so many options is that the one that makes the most sense for any given circumstance has a lot to do with how the house is designed, configured, and where it's located. Next slide. So the first one we're going to look at is placing ducts in an unvented attic. We're starting to see more application of unvented attics really throughout the country. It's prescriptively allowed in the code now. In a lot of circumstances, it makes sense for what we're trying to accomplish. Basically, what we're doing in this instance is taking the thermal boundary that used to be almost universally at the building ceiling and putting it up at the roof plane. And when we do that, we're really just enlarging the thermal enclosure and capturing a large volume of space within that thermal enclosure that gives us the opportunity to place the ductwork. Next slide, please. So when we placed our ducts in a unvented attic space, again, by placing the insulation up at the roof deck, we're utilizing a volume that already exists. What this does for us is it allows us a lot of flexibility in terms of where the ducts can be located. You've got the entire ceiling plane of the house to operate with, basically. We could have supplies where we want them. We can have returns where we want them. You could run the ducts around obstacles and other protrusions within the attic space. So in a lot of instances, it can be a pretty practical approach. It also does give us a place to place an air handler, which a lot of these other options do not provide for us. There are some limitations, however, one of which is that storage is typically not allowed in a space with foam insulation at the roof deck without the use of thermal and ignition barriers and some other safety considerations that are also enumerated in the code. Next slide. Another consideration when looking at the unvented attic approach is the type of insulation and the configuration of the insulation that we're going to use. One of the things we need to keep in mind is that when we do put insulation at the roof deck, in particular in colder climates, we've got a concern with condensation control at that roof deck. The code recognizes it and has a minimal amount of air impermeable insulation that needs to be installed directly against the roof deck, either underneath the roof deck in the form of spray foam insulation, for example, or on top of the roof deck in the form of rigid insulation such as polyiso or XPS or a similar product. That red box is just indicating in zone 4 the level of air impermeable insulation would need to be R15 in order to meet this code requirement. And basically what that's trying to do is keep the first condensation plane, the lower part of the insulation, basically above the dew point so moisture doesn't condense at that point. There's one other consideration here too, that if we are using open cell insulation, which is air impermeable, we'd need to provide a vapor retarder at the bottom surface of it, and that's also indicated in the code when it relates to unvented attic spaces and the insulation requirements. Next slide. Here you can see a sort of a mock-up of an assembly of a unvented attic space with the air impermeable insulation installed directly up against the bottom of the roof decking. That would be say a closed cell foam insulation, and in the climate zone 4 we just looked at would be an R15 approximately. In that instance, the rest of the insulation could be just a dense pack cellulose, a dense pack fiberglass, a netted product, and we've got a code compliant effective system. Next slide. So if we're looking at installing ducts in an unvented attic space for our thermal protection of those ducts, or any other system for that matter, we look at the advantages and disadvantages or limitations of that particular system. In this case, the ducts in the unvented attic does give us a place for the air handler, which is very important. We're not just protecting the ducts, but we don't have to worry about the air handlers in this instance as well. It's not as plan dependent as some other options because, again, as I mentioned, you can put the ducts pretty much anywhere you want on the ceiling plane. The registers can go anywhere. And it's viable for retrofits. I've got an existing house. I've got ductwork in the attic already. I can go ahead and do spray foam and similar applications at the roof deck, and it can work quite well. Limitations. Typically, this is probably the highest cost option for providing a volume to place the ducts in. Roof deck insulation typically costs more, and there's more of it than, say, ceiling insulation. There's code limitations in terms of the vapor retarders and on the condensation control. And by putting the insulation at my roof deck instead of the ceiling, I've in essence increased the size of my thermal boundary, which really does increase the heating and cooling load on the house. And it depends on how much you're increasing it for that sort of cost-benefit analysis to work out. Next slide, please. Okay, the second option we're going to sort of look at briefly is ducts and drop soffits. In this instance, we just basically take the ducts and we put them below the ceiling plane inside the floor plan and sort of integrate them so that they become part of the floor plan themselves. The architectural integration, obviously, and the functionality of it and the aesthetics are really critical considerations, far more so than the unvented attic approach. Next slide. In this plan, you can see sort of an example how the drop soffit would work in one application. Here we've got the air handler sort of in the middle of the floor plan. That's that little X inside the large blue plenum box. We've got the secondary bedroom wing on the bottom of the plan, and there, with a 9-foot ceiling in this house, we were able to drop the ceiling in the bedroom hall wing about a foot, and that just gives us a place to run our takeoffs to those various spaces. On the upper part of the slide, we've got the master bedroom. Just put a dropped soffit sort of cornice ring around the space, and again, that gives us a place to put the duct. So the architectural integration of this application really is one of the drivers. The other thing we got to look at when we're doing this sort of an application is the length of air throw. If I throw the air more than, say, 12 or 14 feet, I really don't get good mixing. So we've got to be careful about how far the register is located from the outside perimeter of the house when we're working this sort of a plan out. Next slide, please. The actual application of that soffit is also critical. Basically, it requires a separate airplane and air sealing application. The slide on the left shows it done with drywall that's taped and mudded prior to the primary drywall getting installed. The slide on the right is sort of a diagrammatic section of another approach where we just use a laminated fiber product like a thermoply, apply it directly to the framing, air seal as necessary, and then build the soffit around it later on. This way we don't have the drywaller coming in for a second stopover, and the framer actually does the installation of the thermoply. So if we do it that way, we can sort of skip a step. We don't have out-of-sequence drywall applications and things of that nature. Air sealing is critical because, again, this is separating the duct space from the attic. Next slide, please. Again, advantages and disadvantages. It's very low cost and simple plans. It's pretty easy to understand and implement. If you explain it to a contractor once, they get it. There's virtually no code restrictions. Limitations, heavily plan dependent, doesn't work in all plans. Advanced planning is absolutely critical, and I mentioned the throw distance is also critical. And there is no provision for an air handler in the soffit unless you get it to one of the skinny hotel type situations. Next slide, please. Okay, the next option we'll look at is a modified truss. And basically this is sort of the inverse of the drop soffit we just looked at. Instead of creating a space below the ceiling plane, we're creating a space above the ceiling plane. And to do that, we're just sort of reconfiguring a standard roof truss to create that volume. You can see the image on the bottom shows what that space looks like actually installed in a house, and then the diagram above shows what it looks like in section with the truss plenum space and the insulation shown, and sort of the relationship of the two. Next slide, please. When we install this truss, we basically have the same steps we do when we've got the drop soffit. So basically the truss gets installed, we've got our extra volume defined where the ducts are going to go, and then we put in our air sealing materials and steps. Again, we found that using a laminated fiber board product like Thermoply really works the best. It's pretty cheap. Framers know how to use it. It's basically, it's 1/8 inch, kind of dimensionless, so you could lap drywall over it and it doesn't get in the way. So it's pretty simple, easy, and cheap. And simple, easy, and cheap is usually pretty good. Next slide, please. Okay, this plan image shows in that house we were just looking at where that plenum space aligns over the second floor floor plan. And what we try to do here is put the plenum space, or the truss space, just large enough so that it overlaps each of the rooms that we're trying to get air to. Then by using ceiling supply registers at the inside perimeter of those spaces, we could throw air towards the outside perimeter and get good air mixing. And it works pretty well. We just have to make sure that that space laps over the spaces we're trying to condition far enough so that we can get a ceiling register into the ceiling of the space that wants the conditioned air. Next slide. If we need to go with a slightly larger plenum space, dependent on floor plan and other considerations, you can get a wider space by using a modified scissor truss, which we've done on multiple applications. In this case, the wider plenum space can be achieved and span larger portions of the floor plan. There's less bends in the air seal product, so it's a little bit simpler to put on. It's a little bit more planar, easier to air seal and tape and mastic. In both cases, both with the scissor truss and with the square space that we saw prior, the ceiling members, the horizontal ceiling members, are actually not structural and are added later on after the space is air sealed, and sometimes after the ductwork is installed as well. Next slide. And here we see a sample floor plan with the scissor truss plenum space. In this configuration, you can see that the wider duct space is created, giving us a little bit more flexibility in terms of where we want to put our supply registers. The other thing that we could do with this plenum space, with the scissor truss or the modified truss that we saw prior, is that the volume created actually can be used as a return air path. If we do use it as a return air path, however, you can't put plumbing, you can't put Romex wiring in it. It basically just becomes a plenum space. So it does have that option, but you have to be careful when you do it that way. Next slide, please. Again, on the advantages, low cost and simple plans. Not as plan dependent as the drop soffit, because you're basically creating a space in the middle of the building, and you could put ducts pretty much where you want in that middle space. Minimal code restrictions. It does work best in linear plans, and that's true for both the plenum, the scissor truss, and the conventional truss. There is that additional air barrier and unique air sealing approach, and it does require custom trusses. But otherwise, it can be pretty simple and can be pretty effective. Next slide, please. Probably the simplest approach that we've used is using open web floor trusses for the integration of the ducts. In concept, it's actually very simple. The space exists if you're using trusses that are deep enough, say 12 inches or what have you. And you just simply run your ducts within that space, the vertical space between the bottom cords and the floor deck, and then use generally floor registers up or ceiling registers down to get the conditioned air into the space. Next slide. The real trick to using this approach is the design integration. I've got a structural floor plan that would be worked out by a truss manufacturer, for example. Then the HVAC needs to be carefully integrated into that to get the supplies where I want them in the rooms, and to work with the truss configurations, because the trusses can't be chopped up like a dimensional lumber would be with headers anywhere you want them. They're specifically designed, and so the plan integration is important. You also want to make sure that the plumber doesn't show up first and try to run his waste lines, because invariably that's where the HVAC guy wants to run his duct. So coordination is absolutely key. Next slide. As I mentioned, typically ceiling registers blowing down and floor registers going up. You can use high wall registers. Typically we've done them on second floors and heating, cooling dominated zones for better cooling performance, but floor registers can work there as well. Next slide, please. Very low cost and simple plans. Basically you're using an existing space and you're not using any existing additional materials. Flexible locations for registers, minimal code restrictions, but really it's the coordination that takes the effort. So advanced planning is probably as important with this approach as it is with the drop soffit approach. Next slide. Another approach would be to use a conditioned basement space or a unvented crawl space. These can work quite well. Basically what we're doing is we're placing the insulation at the wall of the crawl space or the basement rather than at the floor, which actually improves the building envelope performance as well, so it's a good idea to do it. And in this case we do have a place to put the air handling equipment as well. Next slide, please. Again, advantages and limitations. It does improve the enclosure performance because we are putting the insulation where it makes the most sense. In this case, the walls and not the floor of the crawl space. We do have flexible register locations. We can put them pretty much anywhere we want. Same thing with the ducts. There's very little limitations in terms of placement. And all the equipment is serviceable, is accessible for service, which can be an advantage. There are code thermal insulation requirements, and there are code mechanical ventilation requirements. The mechanical ventilation requirements are important to pay attention to, and they can be a little bit strange. We're doing some more research on those right now, but as it stands right now, basically it's 1 CFM of air per 50 square feet, either continuous exhaust or from the conditioned air system within the house. Next slide. And I have about 2 minutes left, and I'm just going to really quickly go over the last option here, and I know Dave is going to get some more detail on the buried duct option. But basically what the buried duct option is just to take the existing the duct system and just lay it on the attic floor, air seal it to the best you can, and then place the insulation over it. Next slide. We started doing research on buried ducts in Phoenix probably around 1998 or so. When we had reluctant builders who wouldn't do the drop soffits we wanted. And this is just a real quick proof of concept study, and you can see the difference between the slide on the right and the slide on the left. The charts underneath each are showing the conductive heat gains to the duct systems in each location. So you can see the chart on the right, essentially there were no conductive heat gains. The chart on the left, the heat gains are mimicking the attic temperature, so there's a clear correlation between the temperature of the attic and what the conductive heat gains in the duct were. Next slide, please. So using that as a concept, we started working in California around 2000 and came up with a methodology and metric for buried ducts that you see here, which indicates deeply buried ducts, fully buried ducts, and partially buried ducts, which indicates specific levels of burial and insulation. This work ended up being for the California Energy Commission, and by 2005 was included as an alternate compliance method for California's Energy Code Title 24. Next slide, please. Using that information, we wanted to sort of apply this approach to hot, humid climates, and we started that research a little over about 2003 or so, and started working in Atlanta and Florida, and came up with the methodology for condensation control on these buried duct systems. Because if I've got cold air going through a duct in a hot, humid attic, sort of like that glass of iced tea in the summer, we're going to get condensation on it. So our research came up with a method of inhibiting that, preventing that from happening. Next slide, please. and then eventually working up a table that shows what the equivalent R value is for different burial types, different thicknesses of insulation, and how to avoid that condensation. This approach now has been included prescriptively in the 2009 IRC, so you can look right in the code about how to do it. And it's also a Department of Energy zero-ready energy home alternative method for conditioned space ductwork. And Gail, I'm going to ask you to skip ahead 2 slides to the advantages, disadvantages one. One more. There we go, because I know Dave's going to get some of the details. So the advantages, disadvantages can be very low cost and simple plans. With the buried ducts alone, it's basically 0 cost, easy to execute, very little plan coordination. The ducts and registers can be anywhere in the attic plane. Compliant with the codes, as I mentioned. Does require HVAC design coordination, and there is no provision for AHU. And the last thing I'll mention before I hand it off is that this process, the buried and encapsulated ducts, was awarded a 2013 Building America Top Innovation Award, which we're very proud of. And with that, I'll hand it off to Dave.
Well, thank you, Bill. It's great to be here to share some of our research on compact buried ducts. Next slide, please. Bill presented a lot of good options for duct installations in conditioned space, but I'm going to focus on a compact buried duct approach and present an overview of the features, benefits, and issues of compact ducts and buried ducts. I have some results from 2 of our projects in the mixed humid climate and details from our current project in a hot humid climate. Next slide, please. So I'm going to dive right in with a little background. The benefits of installing heating and cooling air distribution ducts in conditioned space are well known. The biggest benefit is reduced heating and cooling energy losses due to duct conduction and leakage, compared to ducts in vented attics or crawl spaces or a garage. Locating the ducts and equipment in conditioned space is important to help meet whole house energy saving goals, but can be a challenge for some house designs and for some builders, particularly slab-on-grade houses and 2-story houses with open floor plans or complicated framing. The photo in the upper right shows an open floor plan for a 2-story house where running ducts from the basement up to the 2nd floor was very challenging. Ducts can be installed within bulkheads, dropped ceilings, or floors, but that can get complicated at times and require custom designs. The additional framing and air sealing may not be considered cost-effective by builders, and bulkheads may not be acceptable to buyers in some cases. Building an unvented or sealed attic is an option. That can increase whole house energy use because there's more volume to condition, and they may have less insulation, and those can be expensive to build. Conventional attic ducts, that is ducts above the attic insulation, are a simple solution. Ducts can be installed anywhere, but not energy efficient, especially where the ducts are near the roof deck. Next slide, please. Buried ducts can be a practical and energy efficient alternative to ducts in conditioned space. Also an alternative to unvented attics or conventional attic ducts. Buried ducts are ducts that are insulated, installed close to the ceiling in a vented attic, and covered with attic insulation to reduce energy losses. Locating the ducts in the attic is simple and allows for a standard duct layout approach for different house designs. Energy savings will vary by house design and climate. The heating and cooling energy penalty for conventional attic ducts compared to ducts in conditioned space can be 15 to 25%. That is, the conventional attics can be that much worse. There is a penalty for buried ducts. That can be 5 to 10% or less, which is roughly the same as building an unvented attic, depending on the insulation level. The primary concern with buried ducts is the potential for condensation at the outer jacket of the duct insulation during the cooling season in humid climates. Condensation can occur when the temperature at the duct surface reaches the dew point, and as you know, I think the temperature at which water vapor within the air condenses into a liquid on a surface. That's why buried ducts are more common in dry climates. Also, duct leakage, in addition to energy loss, can aggravate the condensation potential if cold air is allowed to blow onto a nearby surface. Current best practices for buried ducts, those rely on encapsulating the ducts with closed-cell spray foam to control condensation and duct leakage in humid climates. The DOE Building America Zero Energy Ready Home program allows an exception in humid climates for ducts in a vented attic that requires R8 duct insulation, encapsulated with at least 1.5 inches of closed-cell spray foam, and covered with at least 2 inches of blown-in insulation, and then tested to a total duct leakage rate of 3 CFM at 25 pascals per 100 square feet of floor area. Next slide, please. Compact duct. A compact duct layout has shorter duct runs, fewer fittings, and less duct area compared to conventional layouts. This reduces duct pressure losses, improves airflow performance, and reduces fan power. Less duct area also reduces conduction and leakage losses. And of course, those losses are to the outdoors where ducts are not in conditioned space. Less duct area can translate to lower installed costs as well. For energy, incorporating a compact duct layout with a buried duct layout can reduce heating and cooling energy losses by up to 50%. It's simply based on less duct in the attic. Design considerations for compact ducts. A compact central return, that is where the return grill is close to the air handler, is the best opportunity to reduce duct area. Ideally, the entire return trunk is in conditioned space, serves 1 or 2 return grills per level, and eliminates branch runs. As shown in the photo, the lower right corner photo shows a central return within a duct chase that serves the second floor of a house. For these short returns, the designer needs to pay attention to air velocity and turbulence to control noise. For example, there should be at least 2 elbows and 8 to 10 feet of duct between the grill and air handler to reduce line of sight noise, and you may need to consider long radius elbows or turning vanes and even duct liner. The Air Conditioning Contractors of America Manual D provides good guidance for air velocity limits and noise control. Transfer grills can be installed instead of a ducted return to provide a return air path for bedrooms or other rooms with doors. Those should be baffled to minimize sound and light transfer, and an example of those is shown in the photo in the lower left corner. Supply registers can be located to minimize branch duct lengths, for example, in ceilings near an interior wall and away from the eaves, as shown in the photo in the upper right. It's important to select the right register type and location to provide sufficient air mixing, that is to minimize stratification and stagnant zones within a room, and to avoid drafts and excessive noise. Next slide, please. Our first buried duct project was this single-story slab-on-grade house in central New Jersey near the coast in IECC Climate Zone 4A. This was a Building America 40% test house, and the project goals included testing and monitoring of a buried duct system. It consisted of a compact central return in conditioned space, all below the ceiling plane, along with the furnace and bedroom transfer grills. The ducts in the attic were insulated to R8. That was a metal trunk with R8 insulation, flexible ducts, branches, and metal insulated boots. And with limited encapsulation, the trunk was encapsulated and the boots, but not the branches, not the R8 flexible branches. You'll notice a unique design on the upper right photo. There's a duct chase within the trusses. We initially thought we might try to seal that space to make it a conditioned area, but decided that it would be simpler to seal the duct instead and not try to seal that chase. We did install temperature and relative humidity sensors at various duct insulation surfaces as well. The duct leakage test after rough-in for this project measured a tight 1 CFM 25 per 100 square feet. That was for the attic supply ducts only, before spray foam. The duct blaster was attached at the open supply plenum before the furnace was installed. The final duct leakage was a little high, but zero to the outdoors. The leakage was attributed mostly to a leaky furnace cabinet. Monitoring, we did not, no condensation was measured or observed over 2 summers, notably at the R8 supply branches without the spray foam. For this house, the compact design eliminated 70% of the return duct compared to the builder standard and nearly 30% of supply duct and the octopus layout up near the roof deck. And before I leave this slide, I think it's worth noting that the compact central return alone reduced the total equivalent feet of duct from 390 to 263 compared to standard builder design. That's a pretty big deal that HVAC designers will appreciate. That improved the friction design rate from 0.05 to 0.08. Next slide. The second buried duct project was a 2-story house with a basement in Maryland. That's ClimateZone 4A. It has 2 independent systems, both furnaces in the basement, conventional first floor duct layout, and a vertical duct chase that housed the central return, feeding the upstairs, and a supply trunk to the attic. The return is below the ceiling in a conditioned space. Project goals included testing this revised design for thermal performance and monitoring it for condensation. This design up in the attic had a compact supply duct layout as well. The house is 3 rooms deep, so the supplies were located as close to the interior walls as they could be. Has an R16 branch, which is a double R8 branch duct, one inside the other, and standard metal boots with R8 duct wrap. In this case, the metal trunk was encapsulated, but not the branches or boots. The duct leakage test at Ruffin was fair, but was the same before and after the spray foam, indicating that the spray foam in this case didn't help with the leakage control. The final duct leakage was higher than expected. Suspect a combination of leakage around the boots at the ceiling, using tape and not mastic, and a leaky gas furnace cabinet, and interior ducts that appear to communicate with the outdoors through the top of the chase or perhaps through the rim. But despite that, no condensation was measured or observed over 2 summers, notably at the supply register boots. Next slide, please. This graph is a snapshot of a 2-week period where the conditions were closest to condensation at that Maryland test house. It plots the difference between temperature and dew point for 15 sensor locations. The closest was only 2 degrees away from condensation. That was at the top of the encapsulated trunk, but the average differences were much greater during the season. And in fact, even during this worst week or 2, the R8 boots averaged 8 to 12 degrees away from condensation. Next slide. So the results of these mixed humid projects gave us the confidence to proceed with our current project. We'll be installing a compact buried duct system in a test house in Beaufort County, South Carolina, in the southeast corner of the state. That's ClimateZone 3A, but just over the river from Zone 2A, where the average summer dew point is about 72 degrees. The purpose of this project is to build upon previous Building American research to develop a buried duct system that performs effectively as ducts in conditioned space for humid climates. That is one that is durable, energy efficient, and practical to install. One goal is to develop a duct design that does not rely on encapsulation, because we work with some builders that prefer to avoid spray foam and instead rely on more common duct materials and products. Other goals are to incorporate a compact duct layout and identify needed inputs for accurate manual J-load calculations and energy modeling programs. Next slide, please. One of our objectives for this project is to determine the lowest level of duct insulation that will prevent condensation. Modeling was performed to try to predict at what point condensation could occur, but to better understand the moisture conditions within the attic, we installed sensors in an existing house, a builder model home in a nearby community. that included a sensor tree shown in the photo in the attic with sensors at 1 inch, 3.5 inches, 6 inches, and 8.5 inches above the ceiling. Those were installed and then covered back up with the attic insulation. We also installed sensors on 2 ducts at 3.5 inches above the ceiling as well. Those were conventional ducts, so we just tried to capture a portion of the duct that was buried in insulation. Next slide, please. This is actual data from those sensors. Again, we're collecting temperature, relative humidity, and dew point data. This graph plots the dew points during a typical late August couple of days. You can see the outdoor dew point is pretty steady at 65 to 70 degrees. The indoor dew point is steady at or below 55, as expected for 75-degree indoor air at 50% relative humidity. But look at the attic dew points. Those vary from below 50 degrees at night to up to the mid-80s during the day. And the insulation tree sensors in the middle, below the attic curves, show the dew point gradient that rises and falls with the attic dew point, but at a lower amplitude. So the takeaway here is dew points in the attic cycle greatly during the day. Next slide. So we compared the data sets to try to determine if the modeling accurately represents the conditions around the duct. This graph compares the model dew points to the actual dew points at the sensor tree locations. You can see the measured dew points are lower during the day, except at the lowest sensor. The model temperatures did not match exactly, but those were close. Comparing model temperatures and dew points, R8 round duct appeared to be very close to, but not quite at condensation. And by the way, round duct was used for this modeling. The effective R value of round duct is less than flat duct insulations due to the duct geometry. So what works for round duct should work at least as well or better for rectangular ducts. But based on the modeling comparisons, using R8 in South Carolina appeared borderline or even questionable. Next slide, please. But let's take a closer look at the measured data from the model home. This graph shows the dew points of 4 sensors on 1 tree. You can see them up as they progress there during the day, and the duct surface temperature in blue. The duct temperature dips below the 3.5-inch sensor. I have an arrow pointing to that sensor, sensor tree dew point, and one would reasonably expect condensation at that point. But the duct dew point, indicated in yellow on that graph, also at 3.5 inches, just like the sensor, is well below the sensor dew points in duct temperature. Sure enough, I put my hand on that duct about a week later, and it was dry and no sign of moisture. So we know the duct surface temperature changes during cooling, but the dew point also appears to change due to HVAC operation or conditions in the attic or both. Next slide. This is a summary of the compact buried duct design at the South Carolina test house that we'll be installing, planned for this December, next month. So it's a central compact return with jump ducts and transfer grills. Most of the supply registers are near the interior walls. The buried duct insulation, we're going to have an R8.7 duct board trunk, R8 flexible branches, and metal boots with R8 insulation. We're going to have 1 R12 branch run and supplemental at flex connections. What I mean by that is where what I consider the weak link, where the flexible duct is compressed at takeoffs or boots. We're going to monitor the effects of that compression, but also have some supplemental insulation at those points and see what that tells us. The total duct leakage rate for this project is 3 CFM25 per 100 square feet, and this rate meets the current requirements for DOE Zero Energy Ready Home Program and exceeds Energy Star and 2012 IECC requirements. The target duct leakage rate for the attic ducts only is 1. And isolating the attic ducts is important for this project because leakage here, of course, represents energy loss outside the building enclosure and may cause or contribute to condensation. Testing at this point, at this phase, will also allow for resealing if necessary. The attic insulation, we're going to mount R30 fiberglass loose insulation over the buried ducts. We're going to install markers with depth gauges for the attic insulation for quality assurance. Next slide, please. So to summarize, some builders successfully installed ducts and equipment in conditioned space for all of their house designs. And if that's the case, and I would say stick with that. For those facing any of the design challenges we discussed earlier, for the entire house or just portions of a house, the compact buried duct approach could be a practical solution. It could also be a good approach for a ducted mini-split in a retrofit application. Compact buried ducts can be insulated to prevent condensation. In humid climates, encapsulation is a proven approach. Standard products are also available for above R8 insulation, for example, R13 duct wrap. I don't recommend the R8 ducts just yet in humid climates, at least until we evaluate the test house results, which we'll be monitoring that this coming summer. Compact buried ducts can be sealed to within acceptable standards. Again, encapsulation is a proven method. It can be limited, for example, at boots and takeoffs. Conventional sealing methods can work also. Either way, we recommend testing at the rough-in stage to check the duct tightness. Also, compact buried ducts can provide energy savings and comfort, and compact duct layouts alone can benefit any duct system. And our next steps are to evaluate the compact duct layout and monitor potential condensation at the test house during this upcoming cooling season. So that's the end of my presentation.
Thank you, Dave. And our next presenters are Jordan and Francis.
Thanks. This is Jordan Dentz with the Aries Building America team. The first presentation, Bill presented a good case for ducts leakage being a bad thing and why it's a bad thing. And this presentation will cover retrofits and how to combat duct leakage in retrofits. We have taken two technologies or two approaches to sealing ducts in 40 buildings and compared the two. And we're going to go over the results of that and talk about how those strategies were implemented. So as we've already talked about, duct sealing is important. Reducing duct leakage is important from an energy standpoint as well as other reasons that Bill mentioned earlier. But duct sealing can be difficult, costly, and disruptive to do in a retrofit situation. So we compared two techniques, manually applied sealants, which is basically mastic and tape, and an injected aerosol sealant. And we'll get into details about what those are in minutes. So the purpose of this project was to answer a couple of research questions, and broadly, we wanted to understand what the cost and effectiveness was of these two approaches relatively, as well as what logistical and technical issues might affect large-scale implementation of these approaches in the types of housing that we implemented this in, which is low-rise, multi-unit residential public housing complexes. So this is what we're going to go over. We have some modeling results, some building analysis to understand what the implications were in terms of cost effectiveness and payback as well. So the field study. We had two housing developments in North Carolina, 1- and 2-story buildings with central air conditioning and natural gas heating. And we divided them up into two pools. Half of them get the hand sealing approach, and half of them would get this injected aerosol sealing approach. The ducts were a variety of types. They were both flex ducts and metal ducts, both attic ducts and floor ducts, and both in conditioned and outside of conditioned space. And the air handlers were all inside conditioned space. So a variety of configurations. So for the 20 units that we did the hand sealing on, the items that were sealed were the boots, obviously, to the floor or to the ceiling, such as the example here shown sealed with foil tape. The return plenums were sealed from the inside with mastic. And the air handlers were sealed from the outside with mastic. Finally, where accessible, and that's the key point, where accessible, the rigid trunk duct and the trunk to flex duct connections were sealed inside the attic. And that's difficult work, and often where we'll see later the AeroSeal has its bigger benefits. So I'm going to turn over to Francis to discuss the AeroSeal system. Francis, you there?
Yes, I'm here. Thanks, Jordan. And what I'd like to do is start by giving a quick but maybe oversimplified description of the AeroSeal technology. AeroSeal was created from work done at Lawrence Berkeley Laboratories in 1994, and they began doing business as a company in 1997. Some describe the system as similar to being fix-a-flat, which many people recognize as used to plug leaks and inflate flat automobile tires. However, there is one big difference. The aerosol sealant particles are partially dried before they enter the duct system, so they will not stick to the duct walls. And that's pretty important to make this a practical solution for ducts. The sealant is a vinyl material that is suspended in a water solution. The AeroSeal process atomizes the sealant, and then the nozzle directs the sealant particles into the ducts, and they are pushed towards the holes with a high pressure and deposit on the holes. Next slide. The setup is straightforward, but it's a little bit time-consuming. The major tasks are first to seal the supply registers to contain the sealant inside the ducts and prevent it from dispersing into the building. And we typically use compressible foam plugs to do this. Another task is to seal either side of the coil and the other HVAC equipment to protect the equipment from any of the sealant material. So even though it doesn't tend to stick to the ducts, we don't want it to find leaks in the cabinet that we don't want the sealant to accumulate at. And finally, we attach all this equipment together using a plastic tunnel, which is a duct, but it's used to give the sealant time enough to dry before it enters the ducts. And I think we'll see a picture of that next. If we can get to the next page. When the sealant dries, we like to think of it as forming a skin around the beads of sealant. And another bad analogy perhaps is, think about water balloons. So we have a dry surface of the sealant, and there's still some particle inside that is not quite dry. What you see in these two photos is the first one, the very back piece of equipment, is a fan, much like a souped-up duct testing fan. That creates the pressure in the system. The next little box in that first picture is an injection nozzle where the sealant is put into the airstream, and it's coupled with the heater. So the heater will act to dry the particles as they run through the tunnel, which you see in the next picture. Next slide. This system is controlled with a computer that monitors several things: the flow rate of the airstream, the temperature of the airstream, and the humidity levels. And it indicates adjustments that need to be made to the system so that when the sealant is delivered, it's neither too dry or too wet. Either of those will result in the sealant not working correctly. The computer also monitors the sealing progress on the time scale, and it can be set to shut the system off at a certain target. Next slide. As Jordan said, we hand sealed several things that the AeroSeal system could not seal. The return ducts were just simply too small to use the AeroSeal system. So you can see in this photo we're sealing the return plenum with using hand sealing process. In many cases, the AeroSeal can be used to seal return systems. We often use a Y connector in the duct system to split the airstream towards the return and the supply, and sealing both of those at once. The other things that were sealed, I think Jordan already mentioned, is the plenum, the air handler, and where the supply register is connected to the ceiling of the floor. Next slide. I want to talk just quickly about some results. The AeroSeal units improved airflow more than the units that were sealed totally by hand. The return and supply flows both increased in the retrofit units. There was one unit that had a decreased flow afterwards, after we did the sealing, and one explanation that we presume happened was, since this was sealing that was done in an attic, and most of our attics were fairly tight construction, that more damage was done trying to seal that particular duct system by either compressing or kinking the ducts than resulted from the hand sealing. If we look at the next slide, and I'd like to just focus on the middle column because I think that is the most significant. Here we see improvement in the supply airflow using the AeroSeal system compared to the sealing by hand. And we also see the case near the bottom, the next to the last one in that middle column, where the hand sealing actually resulted in a worse condition after than it did before. Next slide. Looking at the last column again shows the average hand sealing resulted in almost 69 or 60% reduction in duct leakage to the outside, whereas the AeroSeal system showed a 91% reduction in sealing in duct leakage to the outside. This is a 32% better than just using hand sealing alone. Next. We also measured just the flows, not just air leakage, but the return and supply flows, which were also increased. In this photo, we're showing a measurement of the airflow with a fan-powered flow hood. This is considered a lot more accurate than the typical flow hood that's used commercially. Return flow, for example, increased by 7%. Again, these were all hand-sealed, but these are how the measurements were made for supply and return. Next slide. The AeroSeal system shows duct leakage in real time as the ducts are being sealed. This graph is a screenshot from the AeroSeal computer. It shows leakage on the y-axis, duct leakage on the y-axis, and the time is shown on the x-axis. I think I'll bring this back to Jordan, who will take you through some of the modeling and some of the economics of the work we did.
Thanks, Francis. One additional point to make on this slide is that while the AeroSeal sealed the ducts to a much tighter level than hand sealing, about 70% of the leakage reduction in the AeroSealed units was due to the hand sealing at the returns, the registers, and the other locations that Francis mentioned. So the balance of 30% being throughout the rest of the duct system that the AeroSeal addressed directly. So just to briefly, we modeled a sample units and plugged in the leakage reduction results that we got from the testing. And this is whole house energy, source energy saving, ranging from 3 to 7% for the various units. As you can see, slightly higher for the AeroSeal units because it's based on a higher duct leakage level. In terms of cost, these were, as I mentioned at the beginning, relatively small homes, about 1,000 square feet each with one duct system. For the hand sealing, there was a difference in cost between the single-story units because in those units, the workers had to climb into the attics to address the leakage there. And, in the two-story units, there were no ducts in the attic. It was between the floors, so those were inaccessible. So the sealing there was strictly at the registers and the air handler and the return. For the AeroSeal, there was a flat rate because it's basically all in the setup of $700 per unit. So slightly more expensive for the AeroSeal implementation. This is a BOP analysis looking at the cost effectiveness. Again, if we look at the annual savings column, the second to the last column, that's the annualized energy expense. So that accounts for all the expense of the retrofit and energy expense annualized over a 30-year period. And the annualized savings ranged based on modeling from about $30 to $70, slightly higher again for the AeroSeal than the hand sealing. But interestingly, both are positive. So both are cost effective from a modeling standpoint. So we also looked at utility bills. And we had a year's worth of utility bills from before and after for most of the units. And these were with the same residents living in the units before and afterwards. And we normalized these utility bills for weather conditions and compared those units that were sealed by hand versus those sealed by aerosol. Interestingly enough, not a huge difference here. Although the aerosol units were tighter, average of 90% reduction in leakage versus 50 to 60% reduction in leakage, they all had about a 15% reduction in heating and cooling energy use. And again, in terms of payback, because the hand sealing was slightly cheaper, there was a shorter, simple payback of over 2 years for the hand sealing and 4.7 years for the AeroSeal. So to summarize some of the lessons that we learned from this little experiment, there are a number of benefits to the AeroSeal system. It allows us to seal inaccessible ducts. It avoids some of the hassles of manual sealing, which include removing duct insulation, cleaning ducts, applying mastic, waiting for it to dry, reapplying the insulation, kicking ducts loose, which is what Francis was alluding to in one of the, suspect in one of the houses. And again, avoid some of the quality control issues of hand sealing. But it does have some challenges. These were small units, which were a challenge to set up the equipment in. It does require this long tunnel, and these were clearance was an issue around the air handlers as well. We were also working in a humid environment, and that created some difficulties with keeping those globules of sealant dry on the outside, as Francis described, and caused some clogging issues. We were able to do all the jobs, but it did take a little longer because of some of these humidity issues. If this were to be ramped up on a production scale, there were some improvements that could be made in terms of the AeroSeal process. A lot of time was spent on setup and cleanup, and most of the time, 70% of the time, the equipment was not actually sealing ducts. It was being moved or set up. So using a Y connector to do multiple units at a time could be a time saver, as well as generally just a scaled down system for all the units would have been helpful. So just some conclusions. Both methods, the AeroSeal and the hand manual sealing, reduced duct leakage. The duct leakage reduction was greater for the AeroSeal, but for the in both cases, the manual sealing areas, registers, the air handlers, accounted for most of the leakage. And the utility bill results were similar, as well as were the BOP modeling results for both methods, both showing that they're cost effective with relatively short paybacks. And I think I mentioned these points already. There's an opportunity to streamline the AeroSeal system for these type of units. And finally, there is a full technical report on this project, as well as a case study available on the Building America website. So that's all I have. Thank you very much. I'll turn it back over to Gail.
Thank you, Jordan and Francis. And we have some time now for a few questions. We already have some great questions from the audience, and you may submit additional questions through the questions pane on your screen. Please indicate to whom you are directing your question, and the speakers will answer as many as time allows. We have a handful of questions for Bill. The first one is, with unvented attics, are skylights still usable? If so, does the skylight shaft need to be insulated?
Well, the answer to that is pretty short, and it's yes and yes. Basically, the shaft of the skylight would be considered an external wall. So whatever the required R value for the exterior vertical wall of that house in that climate zone would be the same requirement for that shaft, and that includes air barriers on both sides of the insulation.
Okay, thank you. And we have a second question here. Could you expand on why air throw distance is so important for the soffit construction option?
Sure. This actually goes into a couple of concepts, and one that Dave went into in a little bit more detail than I did, and that's the issue of compact design. And when you're looking at compact duct design with the drop soffits, I mean, it's integral to it. You want to have as few soffits as possible or practical that have ducts in them, so it'll be less expensive to build and easier to integrate into the floor plan. What that means is that if I've got a room that's 14 feet wide and I've got, say, a high wall register in that space because there's a drop soffit behind it with ducts in it, the air needs to flow at least 12 to 14 feet to the opposite wall in order to get complete mixing in the room. So it really becomes a comfort issue. Now, and the issue is, too, is as we get better building enclosures, the requirement for the BTU output of the HVAC systems becomes a lot less, which means that we have to move a lot less air to meet comfort, which means that each register has less CFM of air going to it. So like a register that maybe at one point with traditional systems I might have 150 CFM, with a high performance enclosure and a compact duct design, I might only have 100 CFM or 80 CFM. And so now that same 80 CFM needs to go a greater distance than it normally would because it's got less pressure behind it. So the distance becomes important really for comfort reasons, and the issues and the problems become exacerbated as we get to better envelopes and compact systems.
Okay, thank you. And then another question is, how does crawl space ventilation requirement impact the thermal losses from ductwork in this location? You referenced 2 CFM per 50 square feet as the requirement. Isn't this larger than the ventilation requirement for occupied spaces?
The requirement specifically is 1 CFM per 50 square feet. So if I have 1,000 square foot crawl space, let's say, that's 20 CFM of ventilation air. And this is a code requirement. I'm not saying it's the right number or whatever, but it's the code requirement. And you could get to that 20 CFM in this case either by continually exhausting 20 CFM out of the crawl space through a dedicated fan, or you can have your HVAC system, if it's a heating and cooling ducted system, designed so that every time the system turns on, 20 CFM of conditioned air is being directed to the crawl space. Not quite sure I get the reference to the rest of the question in terms of the requirement for the rest of the house, but I think that might be referencing the total ASHRAE 62.2 ventilation levels. I'm not quite sure.
And then one final question for you, Bill. What is the approximate incremental cost of employing buried ducts and encapsulated and buried ducts in a vented attic?
Great question, and as I kind of alluded to in my presentation, with just the dry buried duct system that we can do in dry climates without worrying about condensation, really that's kind of a zero-cost option. It just needs to be planned ahead, and if we're smart about it, we can actually save some money, because as we drop our HVAC capacity needs because we've got a more efficient system. Maybe we can save some money on the size of our HVAC system going from, say, a 2-ton system to a 1.5-ton system, which costs less. If I use compact duct arrangements, then there's actually less linear dimension of duct, so that costs less. So you can actually get a cost savings there. On the encapsulated, we found a couple of things. The cost of applying closed-cell foam to the surface of a duct is about $1 a board foot, more or less. So it's about $1 for a 1 by 1 by 1 inch. And with a typical smaller system, compact duct system, probably that would max out at probably about 600 board feet, something like that. So nominally, it would be about a $600 application. What we need to do is make sure that, well, let me say it this way. The guy with the foam truck who's spraying the spray foam typically won't show up for less than $1,000. So if I'm doing a $600 spray foam application on my ducts, probably that's also a good time to spray my band joists and my mud sills and that sort of thing with the same product. In that case, I'm still looking at that, what we would call nominally a $600 incremental cost.
Okay, thanks, Bill. And we have a couple of questions here for Dave. The first one is, can you expand on the design challenges of selecting supply registered for compact duct systems?
Yeah, sure thing. Well, I think that Bill addressed that pretty well. I think the only thing that I would add to that is I think it's even more critical to select the throw in the heating mode. In the cooling mode, if you just reach the exterior wall, you may be okay, even though ideally we design for about 20% more throw than just whether that's from a ceiling diffuser or a high wall diffuser. But in the heating mode, if you just get to the outside wall and don't travel down that exterior wall, at least in the design we used in our South Carolina test house, you'll likely get stratification. You'll have considerably warmer air towards the ceiling in the wintertime, and we tend to have a colder floor, particularly for a slab-on grade house. And that's complicated with if you have a gas furnace, for example, in the house. You're usually running that at a lower airflow, total airflow, so that would compound the problem in the heating mode. At our design house, we designed the throw, which ought to be selected based on manufacturer product data within acceptable noise limits, sometimes referred to as NCEIF noise criteria, or other manufacturers simply state a top velocity, which is sometimes 700 feet per minute. We're designing for throw plus about 4 feet or more down the exterior wall in that case, with the idea that we'll get good air mixing and avoid that stratification. And beyond that, in certain rooms, the designer may simply need to select a different location for that supply.
Okay, and then one other question for Dave. What criteria are you using to determine if non-SPF encapsulated buried ducts in humid climates work? Is minor chronic condensation of any extent acceptable?
That's a really good question. Our goal is to determine the amount of insulation that will prevent condensation. But looking at the dynamic moisture conditions inside the attic, I think it's a good question that may be answered, and that is, if there is some moisture collecting on a surface, at what point does that become a problem? So again, our goal for the project is to prevent condensation, but looking at those dew point curves in the attic and within the insulation, trying to determine what's going on there, it likely could be that if there is some condensation, that it does not cause a problem. But again, our design is to prevent that. And we'll again, we've done some preliminary modeling, and so the next step for us is to actually test some different configurations in that humid climate.
Okay, and then we have a few questions here for Jordan and Francis. The first one is there a recommended materials and process specification for manual duct sealing?
Yeah, Gail, this is Jordan. So in the report that I referenced, we do have a set of specifications just for the manual sealing, as well as specific material recommendations.
Okay, and the next question is compact duct versus small diameter high velocity duct. Are they one and the same, or what are the parameters that differentiate each of them?
I assume that's for Dave.
Oh.
Okay.
Yes.
I can try that. They do have some similarities. The high velocity, the high velocity systems generally do have a single compact return close to the air handler. They do have certainly less area because they're smaller, and they're smaller because they're much higher velocity than a standard conventional air system. So they're not the same thing. I think even though there are some similarities, I think the duct layout would vary because on the high velocity systems, that's driven by you generally need so many, AD supply diffuser for every X number of square feet. You're generally getting about the same volume of air, flow of air from each of those 2-inch inside diameter ducts. So, and they come out at high velocity, so you either need to put them in a corner of a room where they're directed downward from the ceiling. Sometimes they can be put up high in a room, a high wall blowing towards an outside wall, but you have to be, I think, particularly careful with noise and throw for those. They can cause unwanted drafts if they're not located just how the manufacturer recommends those get installed.
Okay, thank you. And back to Jordan and Francis. Did you perform pre and post total external static pressure testing on systems having ducts sealed?
Francis, can you address that?
We did not do any static tests of the systems before and after. No.
Okay, and then another question: what happens to the AeroSeal that doesn't contribute to the seal? Does it enter the rooms and drop out onto horizontal surfaces as a residue? How do you get rid of the excess AeroSeal?
That really is a great question. It was one of our concerns when we first started looking at the AeroSeal system. So if you imagine you have ducts between floors and they're leaking, some of the sealant is going to escape into the living area. And in bad cases, when you have a lot of duct leakage, it will look a little bit like a fog. And there's a couple of things to consider for that. One is we have dried particles, so when the particles settle out, they're dry, they're not sticky. So you may find it looks like sheetrock dust when you've done a sheetrock project on some of your furniture, that there's a residue that you can wipe off. The second thing is, if we anticipate or notice that that's happening, generally we carry HEPA filtered fans. So we circulate the air through HEPA filters. We have a couple of those that we'll put in the space to kind of gather up the particles that have escaped our system and floating around in the house. But yeah, you will see that, and that can be a concern for some homeowners.
And then a related question would be, are there any issues with indoor air quality with AeroSeal, and what type of chemical products are being used in the AeroSeal?
As far as I know, it's a vinyl, and it's considered to be pretty inert. I know LBL did some testing on it, and unfortunately I'm not more familiar with that, but they're not concerned either with the air quality of it, being inside ducts, and they've also done some longevity studies of the AeroSeal material itself inside ducts. And like I said, I don't have the details with me, but pretty much have given both of those a thumbs up in terms of their concerns about air quality and longevity in the duct system.
Okay, and then a final question. Do you deduce that the similar savings found between the two methods is that both sealed high static pressure leaks effectively, or do you think there is another factor?
This is Jordan. I suppose that's a possibility. It may just be that the sample size was not sufficient to capture the true effect, and there might have just been variation, natural variation. But Francis, do you have any thoughts on that?
You know, I think the hand sealing that we did in the attic was above and beyond, I think, what typically you would get, especially in affordable housing. And the fact that these homes have had this type of duct leakage for a long time is because nobody wants to get in the attic and do that work. And you know, it's difficult work to do right. We paid pretty much attention to making sure that they did address the hand sealing in the attic correctly and addressed all the registers, which I don't think is typical. So in my opinion, probably the hand sealing got a little better performance because of the attention we paid to that than it would normally. I think effectively we sealed most of the same holes. You know, I think that's part to answer the question, but I don't think that's typical for the hand sealing. So I don't know if that really answers the question or not, but that's kind of my assessment from what we saw in the results.
Okay, well, thank you, everyone. And panelists, before we take our quick survey, do you have any additional or closing remarks you'd like to make? Nope. Okay, we'd like to ask our audience to answer 3 short questions about today's webinar. Your feedback will help us to know what we are doing well and where we can improve. The first question asks whether the webinar content was useful and informative. To answer, click on the radio button right in the GoToWebinar panel. And the second question asks about the effectiveness of the presenters. And the third question asks whether the webinar met your expectations. Thanks for taking our survey. Stay tuned for the next Building America webinar on December 17th at 3 p.m. Eastern Time. This webinar will review Building America research results. Registration will be available soon on the Building America website on the meetings page. On behalf of the Building America program, I'd like to thank our expert panelists for their time today and to our attendees for participating in today's webinar. We've had a terrific audience and we appreciate your time. Please visit the Building America website to download a copy of the slides and learn more about the program. We also invite you to inform your colleagues about Building America resources and services. Have a great rest of your day, and we hope to see you again at future Building America events. This concludes our webinar.